How many valence electrons does each of the following atoms have? How many valence electrons? So I'm going to listen down. A, titanium. B, iodine. C, radium. And D, manganese. Okay. So for this type of question, to find out the valence electrons, especially if we're dealing with things that are going to be in the transition metals, we have to understand our electron configurations, okay? So we're actually going to have a general one here that we're going to use for all of them. So we'll have the 1s, 2s, 2p, 3s, 3p, 3d, and manganese, just to find out where it is. Having a hard time locating it. Where's manganese? It did actually say, let me just refer to that. 25, I was looking too far. So radium is 80 something. Yep, radon is 86. So where is, oh, radium 88, there it is. Sneaky. And manganese all the way here, 25. So, and we're gonna have now 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 7s, 7p. So this will be how it fully breaks down, because this should account for all the known elements in the periodic table so far. So first one I want to start with is titanium, Z22, so Ti, perfect. So how many valence electrons? It is one of them in the transition elements, but for titanium, as you can see, the way we go through this is we start counting from the top. So hydrogen, helium would count as your first 1s, so that one is complete. So titanium is 1s2. And then we keep going. So lithium and then beryllium, that would be now 2s2 complete. And we just keep counting through. Boron through neon now, that's your P subshell. So that would be 2p6. And sodium through magnesium, that would be 3s2. So this is completed. Okay. And then now we do the same thing here. Aluminum to argon, that's 3p6. And potassium to calcium is 4s2. Okay, so we've completed those. And then now titanium is actually going to be in the D subshell. And as you notice, we actually start with 3D. So it's not going to be a 4. Because when we get to the D subshell, it's going to be whatever row you're on minus 1. So we actually have here 3D2 for titanium, okay? And if we just rearrange that, we have 3D2 for S2, okay? How many valence electrons? We can actually just ignore all the parts that have anything less than 4, because 4 is our greatest number here. It's going to represent the electrons in the outermost shell. So with that being said, we look at the superscript that's attached to the 4s. And the reason why I say 4s plural is that if there are more 4 subshells, if there are more 4 orbitals, we would add up all the superscripts of the ones in that 4 orbital. The only one here we have here is 2. So titanium, okay, would have 2 valence electrons. That would be the answer for that. Now let's use this same sheet to be able to find out about iodine instead now. Okay, so now iodine is all the way over here. It's quite low, and for this actually I'm going to use a different method here, okay, to be able to find its valence electrons, where we actually do what's called a noble gas. You can also just see it on your periodic table. Things like the column 17 is going to be have 7 valence electrons, but I actually want to show that with electron configuration, because this is the best way to go about it, because some will ask about transition metals and some will ask about things that aren't transition metals. So with that being said, the noble gas notation, okay, we actually start with krypton, because that's the previous noble gas. And what krypton has effectively said is that we're actually going to cancel all the way from, because iodine is actually on the fifth, so we're going to actually finish every 4. So this is what we've done so far for krypton. Well, actually not just quite. We actually got all the way to here, about there. And the reason why I say that is because we actually just finished the 4p, that's where krypton is. And now we continue as normal, 5s2, because rubidium and strontium, so that'll be 5s2. And then to pass this whole d orbital, as you can see in the chart, it will be 4d10 based on the chart I showed you. And so that's 4d10, but iodine is all the way over here, so now we're back to the 5th number, so that'll be 5p5, because it stops on the 5th one. Okay, so if we rearrange this, it'll be 4d10 5s2 5p5, and like I said, 5 is the greatest number here, so that would be the last shell. This is kind of what we went through, and we went all the way and stopped at the 5p. So with that being said, 5 is the greatest one, so then we circle the numbers, the superscripts on the 5s, and we add them together. And just like how I said we were going to add them together, we have 7 valence electrons for iodine. For radon, okay, we're going to approach this the same way, where we're just going to use a shorthand. So we're going to actually start with radon for radium. Wow, very similar names. So let's start with radon for radium, okay, where we say Rn like that. And what we've effectively done, kind of like with the iodine, what we've effectively done is said, we're done with this, we're done with that, we're done with this, we're done with this, we're done with that, and we're done with this, and we're all the way over here. That's what that shorthand just meant right there, that we finished all the way to 6p. And now we're going to start with the 7th. So 7s, okay, francium and radium is right there. So we just have 7s2. And just as how we did it for the last one, circle it. That means this one has 2 valence electrons, okay? Now for the last one, manganese, okay? So just erasing all of these. Whoops. Let's just add this back. But now manganese, let's just also use a shorthand just to save us a little bit of time, because hopefully just by at least breaking the tin example, you kind of know how to navigate the electron configuration. So manganese, because the one prior is going to be argon, okay, we're pretty much saying that we're done with this, done with that, done with this, and done all the way to there, okay? So now, for manganese, we have 4s2, and then 3, because remember we jumped down 1 for the d orbital, 1, 2, 3, 4, 5. It'll be 3d5, okay? And that means that for this, we'll reorganize this. It'll be 3d5, 4s2. Manganese then will only have 2 valence electrons, okay? Because it finished that, and then it just hopped into the d orbital, okay? So that's what we have. It's going to be 2, 7, 2, and 2 for this answer, okay? So with that being said, they kind of just went through the where it was in the group, and close but no dice, because manganese in this case would not have 7 valence electron, it will only have 2. So, but the radium is correct, the iodine, oh no, yeah, radium is correct, the iodine is correct, and titanium is also incorrect, it would only have 2, which is why you stress the importance of the electron configuration. This is incorrect, need to use electron configuration. And that is the, I guess, the beauty of it. And you're probably wondering then, if it's, because you're probably noticing a trend here, is that it looks pretty straightforward that your transition metals would just be the valence electrons of whatever is like out here in the first two columns. Most of the time, yes. But then you notice there's some examples, like exceptions, like chromium, for example. Because the d orbital specifically likes to be at least half filled if it doesn't take that much energy, well, you would notice that chromium would actually still have, instead of it being a typical 3d4, it would actually be 3d5 like manganese, but it got its 5 because now instead of we having 4s2, it would be 4s1. So instead of chromium being 4s2 3d4, or I guess if we rewrote that 3d4 4s2, it would be 3d5 4s1, because now its d orbital is half filled throughout, and it prefers that, and it doesn't take too much energy to just use that one electron from its s shell. So something like chromium, for example, would actually only have one valence electron. Just things to be looking out for in regards to this question. And just to make sure that I'm not just making it up, valence electrons for tin. Whoops, that's not tin. That's titanium. That's the trickiest one. Yeah, so this, I would say this is incorrect because it's still basing it off of that. But exactly, you see here, they actually have it wrong as well, because it'll be 4s2 3d2, not 4d2. And here, valence electrons, interesting. But exactly, the configuration is 3d2 4s2. It only really has 2 electrons to work with in the valence shell. So with this, definitely I'll have to do a little more research, because I would hate to be saying something that's wrong, but I am quite confident in regards to at least the valence shell, because when it comes to things with bigger shells, aka like especially the transition metals, they're dealing with different subshells, and that's why, for example, the best way I can say it is that typically you can see tin 4, for example, as an ion, like where it's like 4+, but you also see the option of 2+, because of the fact that transition metals can have difference in terms of their cations, because of the fact that they are transition metals and their valence shell works a little bit more wonky. But we're speaking specifically what it is, it's in its most outer shell, based on the electron configuration, titanium would have 2 and not 4. And same thing with manganese, it would have 2 and not 7. Okay. Then